I would like to start this video by just going back slightly and making some fixes, error corrections, clarifications, replying to comments, and making pledges, actually. Yes, I am recording this after the fact, but I'll put this at the start of the video and add the timestamp if you want to skip to actual content. But yeah, let's start with a pledge. So you may have noticed, I certainly did, that in the last video most of my time was spent grappling with problem statements and not problems themselves. So clearly I'm not being attentive enough and not understanding what's actually required of me well enough. And in the future, and in fact you will see this in this video, do tell me if my reaction seems over the top in this one. But yeah, from now on, I'm gonna try to pay much more attention to problem statements and try to really make sure I understand what's required of me before I jump to propose solutions. Just play around with inputs, try to really nail down what is meant. So that's one thing. While we're on it, I felt I should probably go back to the bus real quick and explain once again my misunderstanding with the problem statement here and what caused it. In general, I'd say I have mostly been convinced that this problem statement is probably fine, although I still maintain that it could be improved, it could be more verbose, it could use some word changes in places. But let's see. So this level has 2-byte inputs and 2-byte outputs. Your goal is to copy from one of the inputs to one of the outputs. Now this 1 and 1 should have probably been my cue. But here's the situation. What I thought when I saw the words the bus, I imagined a situation like this. And this, I felt, is the default state. Just my brain decided that this kind of setup is the default state of a bus. We have input 0, we have output 0, we have input 1, output 1, and the signal just flows through them straight in a ribbon of cables connected to each other, although again I have no idea how this actually works in hardware. And that basically has been my undoing, because of course there's no such implication. There's no implication that this is the default state, right? Now, if I do assume that this is the default state, I hope you can see how I get to my misunderstanding about what copy means here. So let's say we are required to copy from input 1 or input 0. So this is off, and let's say we're required to copy to input 2, right? Now, let's say the input. Okay, I'm gonna go and set it to, what are these bits? Okay, let's set it to 10 just because I can draw a 10 here real quick. So this input is a 10, let's say it's a 10, right? This is an easy number to draw with wires. Now I am required to copy from this input to this output, correct? So what I imagine I need to do is I need to take this 10, I need to copy it, Control C, and I need to paste it, Control V, down here. What this means is I direct the line from up there to down here, right? And I do understand that this has to overwrite the second input-output line, and that's okay. However, there's still a question of what needs to happen to the other output, the one I'm not copying to in this situation. And again, that's where my assumption comes into play, because I assume that the default state for this output is the same as the input. And since I'm not changing the default state, because I'm not copying anything to it, I expected that my output needs to be the same as it was, the same as input 1. But of course, What is really meant here is that the default state of both outputs is 0. There's no such thing as a default thing here. And what really needs to be done is a redirect. Now, you will see this in my actual video, as I pointed out in the next, in the problem statements of some of the future levels. This thing does not actually specify that explicitly. So if you take a look here, your goal is to copy from one of the inputs to one of the outputs. This talks about one of the outputs. And strictly speaking, it does not specify what happens to the other output. This is what you would call an undefined behavior, right? Like explode the galaxy, remove the galaxy, delete the galaxy, you know, corrupt all memory, burn down the PC. In C, for example. Now, of course, there is a reasonable way you can understand these things, a kind of intuitive, logical approach to what should be the case. And it's probably not reasonable to expect these problem statements to always tell you exactly what the input needs to be and what the output needs to be in every sort of permutation. But hopefully you can see that this is not exact. And there is room for confusion. Now, again, since they do say from one of the inputs to one of the outputs, probably you could read that you need to have exactly one output, air quotes, active, with the other one being inactive, meaning 0. And that would make sense. But I still maintain that this word copy is confusing, right? Because what actually happens is I'm not copying this then down here. I am moving it. Come on. I cannot delete. Whatever. I'm moving it down here. Although, I guess you could argue, yeah, that it still remains at the input. But I'm moving it from up here down here because it's no longer up there. And again, in my default setup, there was no such thing as a separation of input and output. This then, in the default case, is the same as this then, right? Because nothing changes. So that's one thing. Now, there's more. There's more clarifications I want to make. By the way, shoutouts to Yotanido. I'm probably pronouncing this wrong. Sorry, but thanks for all the comments. Yeah, this is one of the things that was pointed out, the bus issue. So hopefully I answered these questions. Now, one more thing I'm gonna go back to is a comment about my single bit memory cell, which I generally agree with. I re-implemented the multiplexer right here. However, unfortunately, and yeah, that's, by the way, well spotted. I did not realize that I re-implemented the thing before, but unfortunately, I cannot actually apply your recommendation here. So let's go back to, where was it? Saving gracefully. See, yeah, so right here, these gates implement a mux. Right, they select which signal goes through, this one or this one, depending on this pin. Right, the pin negated and not negated here. And that is indeed the thing we did here with input selector. We do have this mux, 2 switches. However, once we're done with it, turns out we only unlock the 8-bit mux, and we do not have, at this point, we do not have a 1-bit mux. Right? Unfortunately, there's no option to use it as much as I would like to. So that's another thing. Now, a couple more notes going back to the previous levels. I did get comments about optimizations for previous levels, such as reducing NAND scores, which I assume is counted by kind of decomposing complex gates, like an add, for example, right? This add is a single element for me, but really in actual hardware. Oh no, I'm spoiling. Oh no, spoilers, spoilers. Sorry, spoiling the solutions of actual things I'm gonna do later. Yeah, so if you decompose this, eventually it unfolds down to a bunch of NANDs, I assume, and that would be the NAND score. But it's not unlocked, and as you have seen in my first video, I did go to the website and took the recommendation to not try to optimize NAND scores, so I will not be going back to previous levels and trying to optimize them. I do allow myself to play around with stuff and try to optimize it when I feel like it, but I will try to avoid that still, until at least I unlock the NAND score and, you know, feel more at ease with that kind of stuff. And now that I've promised that I won't be going back, I will immediately break the promise, and I will go back to a thing I did way earlier, to this mega binary adder. Oh no, it's not grouped. So nobody actually pointed this out, but I noticed it myself. And this thing, while still technically correct, is very much unoptimal. Here's the thing. Let's take a look at the number of inputs here. We have 1, 2, 3, 4, 5, 6, 7, 8. We have 9 inputs, right? And just to remind you, this is supposed to add once. So the input is not treated as a binary number, it's treated as a bunch of 1-bit numbers. So this would be 1 plus 1 plus 1, 9 times at maximum, right? This means that the output is at most a 9, but in this kind of adder setup, I have 9 output bits, which is a huge number, right? That's 512, right? And I don't need this much. I don't need this much outputs. I only need, so 9 is how many bits? 9 is, I believe, a 4-bit number. So for 9 inputs, I need 1, 2, 3, 4 outputs. That's all I need. And these guys can go. I don't need them. This is my most significant digits. Now, technically, this is not an issue because when adding a 9, they would all just be zeros, and I will be encoding a 1 with leading zeros, so I would have 0, 0, 0, and then like 1 or 8, 4, 2, 1. This would be my 9, kind of. But this is unnecessary, and it's especially unnecessary because I'm using additional gates to calculate these, and I don't need them. And this is kind of important when scaling, because this will I haven't actually counted what the dependence would be, but I think this should grow as n square at the number of bytes, while instead, if I remove all this, really what I have is I have this kind of ribbon shape going down, and the width of this ribbon, it grows down linearly, but the width of the ribbon should grow logarithmically, right? We only need as many rows, air quotes, of additions as we need output bits, which the number of output bits will grow logarithmically as log2. So that's the clarification for this. Again, this was not incorrect, I believe. I believe this is still correct, just slightly optimized. And that, I think, is it for my clarifications corner. And we can proceed with actual levels. So, cut to that. All right. Welcome to all the 3 people who pressed the skip to content button. We are going to proceed, and I think I'm going to proceed with the memory branch because this is self-sufficient, self-contained, while arithmetic still requires unlocks from memory. So I think I'm gonna go saving bytes, then I'll do these two, and then we'll proceed with arithmetic. So let's see. Okay, saving bytes. Create a circuit that can save or load a byte. When the first input bit is green, load the memory and send it to output. When the second input bit is save, or when the second input bit is green, save the input byte. The output has an enable pin, enable it only on load. Huh. Okay, this is quite different from what we did with a single save, right? Because this always output values, while this always output the saved thing. Well, this one, if we're not loading, I suppose they want a 0 output. Well, and there's this enable pin, but we'll think about that later. So, as I promised, I'm gonna try to make sure I understand the statement exactly, and let's test a couple of inputs. So let's say right now load is off, don't load, which means the expected output should be 0. But what if I pipe something into it? That's not. It's not. So I'm guessing these test inputs that I can fiddle with myself don't actually get evaluated as the answer, which is unfortunate. But this I can still test as... Okay, so this is wrong. Action load and save, desired state 17. No, this is not what I wanted to test. I want to test... Don't load. What? Output enable should be on. So it looks like, actually, even though I only have action save, this does not seem to be an error somehow. Can you see it? So does it not care about the output at all? But it says desired state 0, desired output. What are desired state and desired output? I'm guessing output not enabled. Okay, maybe I need to enable output. So let's say my output is constantly enabled for now. I'm guessing this is the enable pin, by the way. Okay, so now there's an output. And now it's not enabled. Aha. Okay, so let's test more. Save. Output enable should be off. Well, see, while I understand this, does it say output enable should be on? Output enable should be on if I'm loading. So yeah, I do necessarily have this on and off, this pin exactly signaling what is happening. And now if this pin is off, then I don't actually care about what gets piped. So, somewhat curiously, I think I might just want to pipe the saved value constantly and then enable or disable this pin as necessary. So let's try and do something like this. Input 1 is load, so I can... Again, I'm still trying to experiment with what's actually wanted of me, as opposed to trying to solve the problem. Because I do find this statement slightly lacking. When the first input bit is load the memory and send it to output. When the second input bit... Well, see, this is, strictly speaking, this is a partial specification. Right? Because when the first input bit is read, is UB, undefined behavior. Destroy the galaxy. Right? When the second input bit is read, UB, destroy the galaxy. So this is confusing. Okay, let's try and test. Like I said, we do have the load pin piped, but it's gonna complain that I'm... Yeah, see? This looks fine. This is not an error. This is not telling me it's an error. The load pin is disabled, but I am piping an output. So it's okay to pipe an output when the load pin is disabled. So I'm guessing this kind of has a switch inside it. Like so. Right? And it basically does this. Kind of. Right? Okay. Okay. So I think I might want to make use of this. Well, at least I don't need to worry about disabling the input or output when the load is disabled. Which, again, would not take me much. Just this as I rode. Alright, so I actually think now I think I'm ready to start actually solving though. Actually, no, you know what? I'm gonna completely exhaust all options, and there's also the question of what happens when the second input bit is read. Well, save is not precisely specified, but it's understandable. And yeah, I'm guessing save equals 0 means come on, why are you not moving? Okay. Save equals 0 means keep saved, and save equals 1 means overwrite save. Right? Like so. Okay, so, as I was just saying, I think this is actually pretty much an optimal solution for the enable pin. However, now we need to save a byte. So I know how to save a single bit, although I do expect to find it confusing still. Let's see, let's reset everything for now. Okay, and I did unlock a 1-bit memory. Save enable, save value, output. Yeah, seems fairly simple though, doesn't it? Just the state of these and we're fine. 1, 2, 3, 4, 8. So again, my saved value goes down like so. And my command save enable, don't save, yes, goes into the top. Oof, I don't like this. Oh well, I will make it neat later. For now, let's just test if this works. So I save, 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 like so. And then these guys can be piped back into a byte maker. And this is going to be my result. They will constantly output. I expect them to constantly output. I never actually tested this, but we'll find out. I expect this to behave exactly in the way that my implementation of it behaved, so let's go. This is correct. Great, we unlocked an 8-bit register. Oh no. The word register gives me assembly flashbacks. Okay, I'm gonna make this neat real quick and I'll be back. Alright, this is gonna be my final solution. Looks good. So yeah, we have one nice save line, just splitting into everything. We have these bits nicely split, and the enable line up here. So that's working really well. I'm guessing let's continue with memory for now. Let's take a look at counter and little box. Counting is so fundamental, even insects do it. I doubt it. I mean, you can assign a behavior of an insect the action of counting. You can see how there is a model of counting in there, evolutionarily developed, but I don't think insects can understand numbers. From counting, species can evolve to compare and do arithmetic. Okay. And before you know it, you have apes building computers. Make a device that counts increments once per tick. What? Does it count increments? Build a counter that will increase by 1 each tick. Additionally, oh. Okay, how large? I am limited in how large of a number I can save, but okay. Additionally, there should be an option for overwriting the counter with a given value. You're given 2 inputs, a bit and a byte. The bit input should toggle between counting and overwriting with the value of the byte. Again, this is underspecified, although I can assume that they want me to store a 1 byte integer and to count in that. And I guess I expect it to overflow to what? To 0? Build a counter that will increase by 1 each tick. Well, my output is a byte, right? Yeah, my output is a byte. And there's an input, and this is count or overwrite. I see. Should be an option for overwriting the counter with a given value. Okay, okay. So, again, I'm gonna take a moment to just reflect on the statement, and I'll be back. Okay, question time. What happens when the bit is set to overwrite? What do I output? Do I output what's saved, or do I output what is being written? Why is watercolor stuck? Okay. So I guess let's try and test that. How? Just wipe this out and see. Add 1, desired output 1. Add 1. No, but keep going. Oh, it cannot keep going. Huh. See? Well, how am I supposed to know? There's no way to know. Do I even output anything? when saving, when overwriting. So I output 0 when overwriting. There's no enable or disable pin in here. Okay, so yeah, it seems like outputting 0 is the most intuitive to me, but this shouldn't matter too much. I think I can figure it out as we go, ad hoc, once I have a solution. I'm gonna find out what's actually required as the output. So I think let's start. I want a bit saved. What? 8. Aha, it has... So this is probably gonna be completely invisible on YouTube, but this up here, this 8, or this red dot, is actually has a small 8 inside it, so I guess that just tells me that load save, I see. Yeah, that just tells me that it's an 8-bit register, byte register. All right, so let's say I have my value saved in here, and the output is count or overwrite. So if this output is 0, then I need to count, which means I basically need to load, right? So something along these lines. Let's just start with this, right? This means I'm counting. This means I'm loading. Also, increase by 1 each tick. Let's check. Add 1. Okay, so I'm actually outputting the value after addition. I don't output what's currently saved and then add. Or no, sorry, it's the other way around. I output what's currently saved and then add. Currently I have 0 saved and I output 0. And then I add 1 and save it. Wait, but I need to load. I always need to load, no matter what. Can I even do this in one register? Huh. Okay, timeout. So basically on every tick, I am both loading and saving to this 8-bit register. I guess let's disregard the overwrite instruction for now, and let's just focus on counting. And when I'm counting, I don't even need this. I'm always saving a new value, like so. Well, there's gonna be addition in here, but let's not worry about that for now. I'm gonna be saving this into itself, and I'm also loading it. Is this even allowed? I'm not sure. Let's test. Also, it's a circular dependency. See, again, this is gonna be... I expect this to be a cause for confusion for a long time for me. But again, the issue of ticks versus gate updates is still weird to me, right? The stuff I talked about where a not takes a moment to actually calculate versus a tick update. So right here, in one tick, I'm loading, and then in the same one tick, can I save at the same time? Or can I not? So let's try some stupid piece of addition here. I should have, yeah, I do have an adder. I don't have a const though. I don't have a constant 1. Oh no, don't tell me I have to. Goodness me. I don't have a constant one. Well, I kinda do, but oof, this is. Oh, I can carry. I can add a carry. Cool. Let's just add a carry. That will work, right? Yeah, that should work. If I just add a... Why is this not deleting? What? It wasn't deleting. Okay, whatever. So I can... Should be able to just add a carry, right? Kind of like so. And then I have one input. And then this is my result. Why are you a bit? You're a byte. Cool. So that's this, and let's try to power this on constantly. So I have a 0 flowing out. Tick 1. So this is not an error. Believe it or not. This is not an error. But what I need to output is, as we've discussed, what's currently saved. So this is actually kind of the solution. Or, well, at least half of it. Yeah, so until the overwrite, I am counting just fine. But I think an overwrite should be relatively simple. I think an overwrite is just a switch, or a mux, actually. Yeah, toggle between two values. I have the result of my addition in the mux, and I have my new overwrite. Except, select 1 to 2. Select 1, 2. Sorry, distraction, IRL, BRB. Sorry, there might be more, but I have time to proceed right now. So yeah, mux, select 1, 2. So red is 1, but I have overwrite as green, so overwrite. So let's say we have overwrite. This means we want to pipe the second one, like so, because I don't want to use a not. And then this is gonna be my situation, right? It's a bit weird that I'm constantly loading and saving, but let's see. Let's test. It works. This worked. Success. Cool. 8-bit counter increments each tick unless overwritten. Wait, what are its inputs? I'm guessing the one overwrite bit and the overwrite value. Okay. So as always, I'm gonna try to optimize this slightly, but also I never really gave much thought, or did I? I don't remember. I don't remember giving much thought to what happens with overflow in these addition things. I mean, we do have a carry out. What if I add... You know what? Let's literally just experiment with this. I can do that fairly quickly. But I'll pause and I'll come back. Okay, so 255 plus 1. What do we get? We get a 0 and a carry. But what happens if I now add 255 and 255? We get 254 and carry. And the carry is just constantly on. Okay. I don't exactly remember, because of course I implemented all this myself, so it's kind of weird to be playing around with it ad hoc, just testing inputs and outputs. But yeah, I don't exactly remember what I did about overflow. I'm guessing just nothing is the answer, other than the carry bit. And there's not much you can do, is there? Cool. So as I said, I'm gonna optimize it, and I'll be right back. This is what I ended up with. This does actually have one structural improvement other than just the looks. I noticed that I can reduce the number of on switches here, or on gates, or whatever you call them, on things, elements. I had 2 separate ones for the loader and the header, but of course one is sufficient. Now, all this said, I'm still not entirely happy with this, because this adder is a ginormous thing capable of adding 2 bytes and factoring in a carry and factoring out a carry. While in fact, all I need to do is increment a byte, and I don't even care about the carry, I just overflow. So I'm tempted to try and build a byte increment thing. I don't think I've built one before. See, I'm starting to forget the previous levels I've done. But I don't think so, right? Byte or, byte not, adding bytes. Yeah, I've added bytes, but I haven't added a 1 to a byte. I have done counting signals, and this is probably what would be the base for my byte increment. I wonder if there's a 1-bit decoder, encoder, sign negator, logic engine, 3-bit. No, it doesn't look like there is. Oh goodness, working computer is pretty close. My. Okay, so like I said, I am tempted to try and implement a byte increment, a ++ operator, which, by the way, this was exactly my question. Is it return x++ or is it return ++x? Right? Of course. Assuming C++, of course, I'm not sure. But that would happen in other languages that have similar operators. So, not C++, I think C has it as well. So, I'm gonna try. I'm tempted to try and do a quick byte increment thingy. But I think I'll do some of it off camera and I'll get back. Alright, so this is my bit increment or byte increment. We have a byte in, a byte out, and this just increments it. This is most certainly smaller than this add, and I haven't actually tested it yet, but let's see. Let's just try a random value. Let's see if, for example, 32 plus 1 is 33. This is 32. 33, cool. 65 I expect, right? Let's add some more. 69, nice. 67. Yeah, I think that's right. 64, 65, 66. Cool. But no, I think this is fairly simple, right? It's self-evident. What's happening here? This is just one line of addition, and I don't care about anything else. Just a single addition to the digit becomes the new digit, and the carry just gets carried down in a single line. So this is a stripped down version of my full adder. However, while we're on the topic of optimization, this on, I'm pretty sure, can also be removed, because we always know that an end with a 1 is exactly the same as the input, so we can remove this and just pipe it directly. While an XOR with a 1 is... what is it? Wait, I'm confused. Yeah, an XOR with a 1 is a negation. We can remove this XOR with a single NOT. over here, or replace. So that's just it. Just as I said. Is this all? There's no way this works, right? Wait, no, I think I'm piping it wrong. Wait, what am I doing? What is XOR? Yeah, XOR is gonna be the negation of this guy. And then AND is gonna be this guy directly. So let's test. You have 0 incremented is 1. Let's say whatever this is. This is the 4 incremented, right? Let's add an 8, so 5 plus 8. I can add 5 and 8. It's 13. Let's add 128. 128 plus 13, 141. Yeah, sounds good. Cool. So we have optimized this. Now I can go back to my byte splitter. Just as I promised I wouldn't optimize things for NAND scores, I decide to go for this hulking huge machine. Okay, I'm not gonna do anything about it other than just remove this add. This on unfortunately has to stay for my save and load. Although, again, I think decomposing this 8-bit register might allow me to remove the constant on. But yeah, so the input is gonna be this way. Don't worry, I saved the original solution in a different schematic. And this is gonna go like so. Let's test. Success. I don't need this AND as well. The final carry doesn't get carried anywhere. So this is what we have. GG. It does seem like it's testing all the possible values of a byte. 8-bit counter. Onwards. Aha, so this piece of memory is still locked, right? Because we need to do a 1-bit decoder. 3-bit decoder. So I guess we're gonna go for arithmetic next time. And 1-bit decoder I will save for later as well.